Hi again everyone. Well, it's been a while since I've done one of these electronics tutorials, but I'm finally back. I have had a busy year, but I've had some requests to get back into it, and so here I am. What I thought I'd do with this tutorial is have a look at the BJT as a switch, which is a practical application of using a BJT. You may have watched my previous BJT tutorial, which had a look at the internal workings of one of these transistors. We looked at the PN junctions inside there and how we actually forward bias the base emitter to vary the collector current and things like that. If you haven't seen that tutorial, go check it out before having a look at this one. I would recommend. Also, I'm going to be doing some calculations. So I've got my calculator here. I've got a calculator tutorial just with respect to dealing with these electronic calculations, and because we're going to be using some resistors, I've also got an Ohm's law tutorial, so I checked that one out as well. Alrighty, so the BJT as a switch, very, very handy to use a BJT as a switch, but I guess what does that mean exactly? Well, if we want to use a BJT as a switch, all we're really doing is we're getting some kind of circuitry. So let's say we've got a microcontroller, and we want that microcontroller to turn on, let's say, an LED. So what we could do is we could connect one of these pins of the microcontroller, let's say this very end one, to the LED, and then we could turn the LED on by sending out a voltage to it, or sending out, in this case, we're going to put 5 volts on the port pin to turn the LED on. But let's say that this LED, or for this LED, we wanted, say, 50 milliamps of current to flow through that LED. Well, this port pin can't handle 50 milliamps, so there's no way that we can turn this thing on and expect to have 50 milliamps running through it. Therefore, what we do is we connect the port pin of the microcontroller to the transistor. This turns on the transistor, which only needs a little bit of current to actually turn that on. When we turn that on, that will be then connected to the LED, giving us our, let's say, 50 milliamps of current. So, in answer to the question, why would we use a BJT as a switch? Well, the answer is, in order to be able to allow a low power device be able to control a high power component, in this case an LED. Alright, so with this little demonstration we'll do here, there's going to be a couple of hypotheticals, or a couple of bits of pretending. So what I'm going to do is I'm going to pretend that this microcontroller port pin can only handle up to 1 milliamp of current. So let's just pretend that. Then we want this microcontroller to turn on this LED, and let's say that we want, I don't know, let's say we want 20 milliamps to flow through the LED. Well, 20 milliamps is certainly bigger than 1 milliamp, and that's all that this port pin can handle. So that's where our transistor comes in. Our transistor will connect to the port pin, we'll turn the transistor on, that'll connect to the LED to turn that on. So let's go through a bit of an example. Here's our transistor. Collector, base, emitter. Let's get that out of the way for a second. What we're going to do is we're going to connect the emitter to ground. We're then going to get a certain value of base resistor and connect it to the base. The other side of it goes to our port pin. Now this port pin, if you haven't done any digital stuff before, this port pin can be one of two voltages or one of two states. It can be plus 5 volts, that's a logic 1, or that's what we call a logic 1, or it can be 0 volts. We call that a logic 0. So we can either put 5 volts there, or we can put 0 volts. To complete this circuit, we're going to, and I haven't really left myself much room here, we're going to connect our LED, the cathode to the collector. The other side is going to go to our power supply, plus 5 volts. So there's our complete circuit. When we put plus 5 volts here, that's actually going to turn on the transistor. If you recall from my last tutorial, if we make the base more positive than the emitter, we can turn that on. And then that is going to give us some collector current flowing through here. And that collector current, with this particular transistor that I've chosen, it has a beta of 220. Now you may have recalled that beta is gain. That means that, let's just pretend that there's 1 milliamp of base current flowing. That means there's going to be 220 times that flowing in the collector, which is where our LED is connected. So therefore, 1 milliamp of base current gets amplified by 220 to give us 220 milliamps here. So the current in the base, and therefore the current in the collector, is all determined by this little guy, this resistor that we put here. So let's, what have I got here? I've got a couple of resistors on hand. What's this one? So I've got a 47k resistor here. Let's do some calculations and see how much current this 47k resistor will give me. So 47k. In order to figure out the current going through the base, we need a couple of things. So remember Ohm's law, V on IR. If we want the current, we're going to need voltage and resistance. So that means we need the voltage across that resistor and the resistance of that resistor to find the current going through it. Now, a base emitter junction, or a forward bias base emitter junction, is going to have what's called a forward voltage drop, and that's in the previous tutorial. And it just so happens that the forward voltage drop of this one is around about 0.55 volts. So if we're dealing with a 5 volt power supply and our base emitter is going to grab around about 0.55 of that, that's going to leave the rest, which in this case 4.45 volts, on the resistor. So 5 volts, take away 0.55 volts, equals 4.45 volts. So now we know the voltage across that resistor, we know the resistance of that resistor, now we can get the current. So the base current, IB, equals 4.45 volts divided by 47k. Let's do that on our calculator. Let's get that out of the way. Oop, it's a bit bright. So, 4.45 divided by 47k. So that gives us 94.68 to the negative 6, so that's microamps. 94.68 microamps. So that's well within limits, because we've just said that this port pin can handle up to 1 milliamp. 1 milliamp is actually equal to, or it's the same as saying 1000 microamps. Where, with this value of resistor, we're only sitting at 94.68 microamps. So we're well under the 1000 microamp limit. So that is all good as far as the microcontroller is concerned. But how much current does that give us through the collector? Well, as I was saying before, to figure out this collector current and therefore the current through the LED, we just need to multiply it by the gain of the transistor. To get that gain, you just have to look up the data sheet for your particular BJT transistor. So, collector current, IC, is going to equal the base current we just found, 94.68 microamps, multiplied by the gain, which is 220 for this particular transistor. So there it is, 94.68 micro, multiplied by 220. And what do we get? 20.83 to the negative 3. So that's milliamps. 20.83 milliamps. So that's pretty good because we were aiming for 20 milliamps. With all these calculations, we found out that this particular resistor will give us 94.68 microamps of base current. That then gets multiplied by 220 through the collector to give us 20.83. So that's pretty good. Let's connect it up and see if we actually get these values practically. So let's get these out the way. In order to do this, I'm going to use my little breadboard. Let's just zoom in here. Hopefully you can see that all right. Okay, so I've got my breadboard, and actually this is one of my Kickstarter projects I put on, the PIC Arduino. It did pretty well. It's just got an Arduino and a PIC microcontroller built into the one little circuit board. Okay, so all I'm using the PIC Arduino for is to give me a plus 5 volt power supply because it's connected to USB here. Here's my transistor. Let's plug that in. So I've got to the left the emitter, in the middle the base, to the right the collector. We're going to connect this up exactly as we see here. Instead of actually using a microcontroller port pin here, I'm just going to connect that to plus 5 volts, just so we can see the amount of current here and then how much current it gives me here when I actually put 5 volts there. So back to this. What I'll do first is I'm going to connect the emitter to ground. So my emitter is this one all the way at the left. Let's get a wire there, and ground is anywhere down on this bottom row. So the emitter is now connected to ground. Second thing I'll do is I'll get my 47K resistor, and this is going to go from the base to plus 5 volts. In this case, I'm going to connect it to the base. So remember my base was in the middle. Oops, I just bent it. There we go. So it's connected to the base in the middle there, and then I've just connected to a blank spot here. And then I'll connect a wire from that, I just bumped the camera, to plus 5 volts. This top row here is plus 5 volts. Okay, so that completes the emitter and base circuit. Sorry, I keep bumping the camera on you. Now the last thing to do is to connect up the LED. The cathode goes to the collector, the anode goes to plus 5 volts. So the cathode in this one is the shorter leg, anode is the longer leg. So let's connect this one up. I'm going to connect the cathode to the collector, just as I have here. So there's the collector, and cathode is in the same row of holes. The anode I've just connected to a blank space, which then allows me to go to plus 5 volts, which is this top row, and then connect that over to there. Now you can see I've got a nice blue LED. Nice and shiny. Let's check out the current. Here is, let's just bring this to there, that'll do. And let's bring this up a bit so you can see a bit more. Okay, so let's see if we get the same amount of current as what we were looking for. Our calculations, we got 94.68 microamps of base current, 20.83 milliamps of collector current. So let's see if we actually get that here. First thing I'm going to do is just disconnect this wire from the base, just so I can put my multimeter leads in to replace that wire I took out. So the black one to the resistor, the red one to plus 5 volts. So it's exactly the same circuit, but now the current is just going through my multimeter as well. And it's telling me, so it's a little bit off what we calculated, it's telling me we've actually got 86.6 microamps. We calculated 94.68. So, I mean, in the grand scheme of things, when we're dealing with microamps, it's only off by around about 8 microamps, which is not so bad. The reason it could have been off is a number of reasons. The resistor here may not be exactly 47K. The voltage drop across my base emitter junction may not be exactly what I said, 0.55 volts. And the last thing is the 5 volt power supply here may not be spot on 5 volts. But all things considered equal, that's pretty close to what we want. Let's connect the base circuit back up as it was. Now let's check out what we get for the collector current. So I'm just going to disconnect my 5 volts from the LED, replace it with my multimeter, and it's giving me an overload condition. I'll change it to milliamps, and we're getting 19.5 milliamps. We calculated 20.83, so in this case it's really only about 1 milliamp off where we wanted it to be. So it's a little bit lower, which makes sense because our measured value was lower than the calculated value, so it makes sense that, again, the measured value of collector current would be a little bit less than what we want. So that's pretty good. So we know that we only had around about, 86 microamps flowing in the base, and our microcontroller could perfectly handle 86 microamps, no problems. Then we found, when we connected it to the transistor, that the collector current gave us around about 20 milliamps, so 19.7. Now, if you recall, I said at the start, we'll just pretend that this microcontroller can only handle up to 1 milliamp. So therefore, we could make this microcontroller handle even more than 1 milliamp by letting the transistor do all the heavy lifting for us. So in practice, microcontrollers could probably handle 20 milliamps. But what if we wanted it to control a motor that required an amp or 2 amps, or if we wanted really high brightness stage lighting, or something that really required a lot of current? Well, the principle's the same. The microcontroller could only handle, let's say, 20 milliamps. We then want to connect it to a motor that wants to be able to draw 1 amp. We would just get another transistor that could handle up to 1 amp. So the last thing I'll leave you with here is, I guess, calculating in reverse. Let's say that you wanted, let's get a new piece of paper here. Let's say we want 100 milliamps of current to power up our device. So 100 milliamps in the collector, because that's where our device is connected to. So how do we figure out what value of base resistor we need to get? Well, what we do is, here's our circuit, remember. Let's say we've got a really bright LED we want 100 milliamps going through. So we need to figure out this guy. What's he going to be? Well, if I stick with my beta of 220, we can easily go in reverse. What we need to do is, we need to figure out what IB is. So IB in this case is going to be 220 times smaller than my collector current. If I want 100 milliamps, then all I need to do is go 100 milliamps divided by 220. So 100, oops, let me do that so you can see it a bit better. Let's bring this up, sorry about that. So 100 milli divided by 220, that gives me 454.54 to the negative 6. 454.54 microamps. So negative 6 being microamps. So that tells me how much current I would have here. So that's all well and good. That tells me the current, but what about the resistor value? Well, if we go back to Ohm's law, in order to get resistance, we need two things. We need the voltage and we need current. We've just found the current, so that's all good. What's the voltage across here? Well, if you recall, I said that we're going to lose around about, and again, you'd look this up in your data sheet for your transistor, but for most common transistors, you're going to lose around about 0.55 volts across the base emitter. If I'm sticking to my plus 5 volt power supply, that leaves me with 4.45 volts. So now I've got the voltage across the resistor, I've got the current. Now I can find out what resistor value we need. So the base resistor RB is going to equal 4.45 volts divided by the current that we're going to have through there, 454.54 microamps. Therefore, our base resistor needs to be 4.45 volts divided by 454 micro, around about 9.8 K. So that's how you can work out what value of base resistor you need in order to get the collector current you want to drive something, in this case that's 100 milliamps. If you wanted 1 amp, all the formulas, all the calculations would all be the same. Alright, well, that's about it for this video. Hopefully you found it useful and interesting. And thank you very much.